So, let us start the next topic of this liquid mixtures. Last class we have discussed about partially miscible liquid pairs. Liquid mixtures are three types: partially miscible liquids, completely miscible liquids, completely immiscible liquids. In this partially miscible liquids, last class, in the last video, we have discussed three types of partially miscible liquids. Partially miscible liquids becomes completely miscible at a particular temperature. That temperature is called critical solution temperature. So, this critical solution temperature, sometimes it is less than atmospheric temperature, sometimes it is higher than the atmospheric temperature. So, sometimes there are two CSTs, lower CST and upper CST. So, a partially miscible liquids having lower CST, we have having upper CST, nicotine, phenol water system for upper CST, phenol water system. For lower CST, we have discussed triethylamine water system, and for upper and lower CST, nicotine water system, we have discussed this in detail in the last video. Let us discuss this miscible liquid pairs today in detail. This miscible liquid pairs means whatever may be the proportion, they are soluble with each other. That is because of the intermolecular attraction between the two liquids. Actually, in this liquid mixture, we are discussing about binary liquids, liquid mixture containing two liquids, binary liquid mixture. So, when you take two liquids A and B, these two liquids, they are completely miscible, irrespective of the proportion. They are completely miscible. That is because intermolecular attraction between A and A, attraction between B and B is similar to attraction between A and B. So, because this intermolecular attraction between these two molecular is similar to the intermolecular attraction of AA and BB, these compounds, these liquids, they are completely miscible. These completely miscible liquids is not ideal. Some of them are ideal solutions, or some of them are not so ideal. So, therefore, depending upon their ideality, what is an ideal solution? An ideal solution is one which obeys so this miscible, completely miscible liquids can be classified into three types. Which obeys Raoult's law. The liquid mixture which obeys Raoult's law at any composition, at any temperature is called an ideal solution. So, many liquid mixtures are not ideal. Some of them are ideal, those which obey Raoult's law. Raoult's law says that the partial pressure of a component A in the mixture is equal to its partial pressure of A in the mixture is the product of its vapor pressure in the pure state multiplied by its mole fraction. So, any component in the mixture, if it obeys this law, this Raoult's law, is an ideal solution. Therefore, these liquid mixtures, they are not ideal some of them have some deviation from Raoult's law. On the basis of this deviation, we can classify this as liquid mixture having positive deviation and which obeys ideally, and negative deviation. Therefore, these completely miscible liquid pairs can be classified as ideal solution, a solution having positive deviation from Raoult's law, solution having negative deviation from Raoult's law. In this ideal solution, irrespective of the composition, they are soluble with each other and they obey Raoult's law at any composition, at any temperature. Now, let us see these type of liquid mixtures one by one. If you can draw the vapor pressure versus composition curve. Let us see what is vapor pressure. Vapor pressure, if you take any liquid, what happens? Above the surface of the liquid, there are vapors of this liquid. So, this is the liquid layer. So, liquid molecules, they go into vapor state, So, therefore, these vapors, they exert pressure. This is called vapor pressure. This vapor pressure increases as the temperature increases. If you go on increase the temperature of the liquid, the vapors here increases, hence vapor pressure is increased. Therefore, this vapor pressure, it directly depends on the temperature. So, now if you draw a graph of this vapor pressure and composition of the binary liquid mixture, what type of graph you will get? Now, this is the composition of two liquids, and this is the vapor pressure and this is the composition. Now, consider two components which show ideal behavior are completely miscible, which obey Raoult's law. This is less vapor pressure, let us say this is more vapor pressure component. One example is benzene and toluene. Toluene has less vapor pressure and benzene has got more vapor pressure. Now, this 100% toluene, this toluene has got less vapor pressure when it is pure, and this is benzene which has got high vapor pressure. Vapor pressure is high when it is pure, 100%. Benzene is highly volatile and vapor pressure is more. Vapor pressure of benzene is more. Vapor pressure of toluene is more. Now, you go on mixing benzene to toluene, 5%, 10%, you go on mixing. What happens to the vapor pressure of the mixture? If you draw the vapor pressure of the mixture, when you change the composition, you will get a straight line like this. So, you take at any composition, you will get the vapor pressure of the mixture. So, this is nearer to ideality. So, benzene and toluene mixture, they obey Raoult's law and they are nearer to ideality. As the composition of the benzene increases, the vapor pressure increases and you will get a straight line like this. So, this is the Px curve of benzene toluene system, vapor pressure of benzene toluene system, vapor pressure versus composition. Now, if you see another type of liquid mixture, completely miscible liquid, example ethyl alcohol and water, Comparatively, ethyl alcohol is highly more volatile, or it has got high vapor pressure when compared to water. So, now this less vapor pressure is water. and more vapor pressure is ethyl alcohol. So, ethyl alcohol comes this side and water comes this side. When you go on increasing the proportion of ethyl alcohol, composition of ethyl alcohol, this is 100% water, this is 100% ethyl alcohol. 100% ethyl alcohol has got high vapor pressure, water has got low vapor pressure. But one speciality is there. What is that? At a particular composition, the vapor pressure gradually is more than water. If you draw a graph of, you will get like this. At a particular composition, suddenly what happens? Vapor pressure increases. This mixture of this water, this ethyl alcohol, this is water, this is ethyl alcohol. Ethyl alcohol has got a high vapor pressure, water has got a less vapor pressure, but at a particular composition, this composition is 96% ethyl alcohol, 95.5% ethyl alcohol and 4.5% water. At this composition, around 95%, at this composition, suddenly what happens? The vapor pressure of the mixture increases. So, at this composition, 95.5% ethyl alcohol and 4.5% water. This particular composition, what happens? This particular composition has got high pressure, even it has got high pressure higher than ethyl alcohol, pure component, ethyl alcohol itself. So, this deviation from this ideal behavior is called positive deviation from Raoult's law. So, that particular composition has got higher vapor pressure, and that composition where the vapor pressure of the mixture is higher than any of the component, that is called azeotropic mixture. Azeotropic mixture. So, azeotropic mixture has got higher vapor pressure when compared to any one of the components in the mixture. So, this is one speciality so there is the deviation, positive deviation from ideality, positive deviation from Raoult's law. Example, water and ethyl alcohol. There is one more type of graph you will get. If you draw graph of another type of liquid mixture, that is hydrochloric acid and water, what happens? The mixture of hydrochloric and water is not ideal, there is deviation from ideal behavior. If you draw a graph, what happens? First the vapor pressure decreases and then increases. First vapor pressure decreases and then increases. There is a decrease in the vapor pressure. This is negative deviation from Raoult's law. There is a negative deviation. That type of mixture is, example, hydrochloric acid and water. If you take this mixture, what happens? When you increase the composition, vapor pressure decreases at a particular point and then increases. So, this is negative deviation. Therefore, we can classify this completely miscible liquids into three types. Liquid mixture which obeys Raoult's law, type 1 liquid mixture, type 1. Example, type 1 benzene and toluene. Second type of liquid mixture which shows positive deviation from Raoult's law. Example of that mixture is ethyl alcohol and water. Third type of liquid mixture is which shows negative deviation from Raoult's law. Hydrochloric acid and water, you can take the example. So, there is negative deviation from Raoult's law. So, three types of curves. These curves are called px curves. Three types of px curves we will get for this liquid mixture: ideal behavior, positive deviation and negative deviation. If you see the boiling point curves of these three types, what you will get here in case of boiling point curves boiling points versus composition of these three types, boiling point, and composition curve. These types of curves are called TX curves. TX curves, this PX curve, vapor pressure versus composition, PX curve. If you see the TX curves of this, what happens? When the vapor pressure is more, boiling point is less. Therefore, for benzene and toluene, you will get a curve like this. So, this is less vapor pressure and this is more vapor pressure. For example, this is boiling point is this is toluene and this is benzene. Benzene has got less boiling point when compared to toluene, and when the composition of benzene increases, the boiling point of the mixture goes on decreasing like this. Whereas, in case of this is for type 1 liquid mixture, example benzene and toluene. For type 2 liquid mixture, what happens? If this particular composition has got low boiling point, type 2 mixture at that particular composition. So, this is less volatile, less vapor pressure, ethyl alcohol, and more less vapor pressure, water, and more vapor pressure, ethyl alcohol. If you draw the curve, it will be like this. So, at a particular composition, boiling point of the mixture is less. This is type 2 liquid mixture. At a particular composition, as I told you earlier, this composition 95.5% ethyl alcohol, 4.5% water. That particular composition, what happens? Boiling point is less in case of type 2 liquid mixture. Similarly, for type 3 liquid mixture, what happens? The boiling point will be more than any one of the components. It will be more than any one of the like this. So, this is type 3 liquid mixture. Therefore, boiling point of this composition, in case of, for example, hydrochloric acid and water, 20% of hydrochloric acid, 80% water. Now, this is the boiling point. Boiling point is higher than any one of the components here. But in this case, boiling point is less than any one of the component, like this. So, therefore, this is the TX curve of three types of liquid mixtures, and this is the PX curves of liquid mixtures. Now, we have to study in detail the distillation of these three types, distillation curves of type 1, type 2, type 3. Type 1, type 2, type 3, the distillation curves. Let us study the distillation curves of these three types. In case of distillation of type 1 liquid mixtures, example benzene and toluene. So, let us take this mixture and let us what happens when you heat this, when you distill this, what happens. So, in this case, let us draw the TX curve. Now, this is benzene, less volatile, this is more volatile, benzene. Now, if you see the distillation curve, it will be like this. So, this is the ideality. In the vapor, what happens at any particular temperature? This is the boiling point. At any temperature, what happens? You see the composition. So, at this temperature T1, in this mixture, this is the composition of benzene and toluene. This is benzene and this is toluene. Now, you see the composition. This is the composition at T1, composition of amount of toluene and amount of benzene. This toluene, this is benzene, amount of toluene, amount of benzene. Therefore, at a particular temperature, more volatile component is more and less volatile component is at the same temperature. Therefore, if you see at temperature T2, you see here almost, so this is the composition of less volatile, that is toluene, and this is benzene. So therefore, in the vapor phase, the amount of more volatile component is more when compared to less volatile component. Therefore, if you take this component, this distillate, and again you distill it. If you go on repeating distillation, the amount of more volatile component goes on increasing. You repeat the distillation, at each trial what happens, the amount of benzene goes on increasing. So therefore, by repeating this, it is possible to completely separate this more volatile benzene from toluene. So this is called fractional distillation. So by fractional distillation, we can separate these two components, more volatile. For that, what you have to distill it repeatedly, several times. So therefore, instead of distilling every time, we are using a new technique, that is called fractional distillation. So this is the fractional distillation method in which these ideal solutions can be separated, because at a particular temperature, composition of one is more than the other. More volatile component is more when compared to less volatile component. Example, if you take benzene and toluene, if you distill it in the first distillate, benzene amount is more when compared to toluene. That distillate again you distill, the amount of benzene goes on increasing. By repeated distillation, it is possible to completely separate benzene. So this is the fractional distillation of this type of liquid mixture. What happens here? You take benzene and toluene liquid mixture, benzene and toluene, and if you heat, what happens? In the first fraction, the amount of benzene is more when compared to toluene. Then what happens if you continue heating? What happens? It goes to the next fraction. In this fraction, again the amount of benzene increases here. It is more than this. If heating is continued, when you come to this phase, this fraction, this completely pure benzene. Completely pure benzene vapors are there. These benzene vapors, they are passed through a condenser, water cooled condenser. Water is passed here, this water cooled condenser. This vapor gets condensed and you will get pure benzene here. Pure benzene. First benzene comes out, leaving behind toluene. So this is fractional distillation. Instead of distilling several times on the basis of this technique, it is laborious. Therefore, this new technique called fractional distillation method is used. Different types of this fractionating column, different types of fractionating columns, they are used depending upon the liquid mixture, and completely those two components can be separated. Ideal mixture, ideal solutions, ideal binary solutions can be separated by this fractional distillation. That is about the distillation of type 1 liquid mixture. Type 1 liquid mixture, which is ideal, and the composition of that is the vapor pressure that depends on both the components, but can be separated by this fractional distillation method. Now come to the distillation of type 2 having positive deviation. Example is alcohol and water. This alcohol and water, ethyl alcohol and water is a mixture, binary liquid mixture, binary ethyl alcohol and water. Ethyl alcohol and water. Type 2 liquid mixture having positive deviation from Raoult's law. How to distillate, how to separate this type of liquid mixture. If you see the graph, what happens? There is positive deviation, and if you draw the Tx curve for this type of liquid mixture, what happens? You can see the graph like this. You can see the graph like this. So at this particular temperature, the composition of ethyl alcohol and water is constant, So this is less volatile, this is more volatile. More volatile means this is ethyl alcohol and this is water. If you draw the boiling temperature curve, boiling temperature, and this is the composition curve, this is the vapor phase, this is vapor phase, this is liquid phase, vapor phase and liquid phase, this is vapor phase. So this is the vapor phase of water, this is vapor and this is liquid water, this is vapor. And if you come to this liquid ethyl alcohol, vapor pressure and liquid phase of ethyl alcohol. Now you draw any temperature at T1, what happens? This is the composition of liquid form and this is the composition of vapor form. In this vapor, both ethyl alcohol and water will be there. Here ethyl alcohol and water will be there. What happens if you go on heating? This is the, you see the temperature. You see the temperature of this mixture. Of this mixture, the boiling point of the mixture is less. The boiling point of mixture is less when compared to any one of the components. Either water or ethyl alcohol, the boiling point of this composition is less. Therefore, when you heat the mixture, first the vapors of this composition will come out. This is called azeotropic mixture. Azeotropic mixture. So azeotropic mixture has got less boiling point when compared to one of the components. So boiling point of azeotropic mixture having positive deviation, type 2, having positive deviation, boiling point of this composition. In case of ethyl alcohol and water, what is the composition? Water is 4.5% and ethyl alcohol is 95.5%. So this composition 95% ethyl alcohol and 4.5% water, that is the composition. This composition has got the lower boiling point. So therefore, when you distill the mixture, what happens? First the azeotropic mixture will come out. And then the excess of the component, whether it is alcohol, water or alcohol. So therefore, while separating the liquid mixture of type 2, you can separate it to only two types. What is that? Azeotropic mixture and one of the components. Suppose if you take 50% water and 50% ethyl alcohol, what happens when you take this mixture? Now, azeotropic mixture of these two is 95.5% ethyl alcohol and 4.5% water. Therefore, this ethyl alcohol, 50% ethyl alcohol takes 2.25% water and it forms azeotropic mixture. 52.25% azeotropic mixture and 47.75% water. So it will separate into these type of components. When you take 50-50 mixture, 50% water and 50% ethyl alcohol, azeotropic mixture of water and ethyl alcohol is 95.5% ethyl alcohol, 4.5% water. Therefore, this 50% ethyl alcohol takes 2.25% water and it forms azeotropic mixture. This is azeotropic mixture and this is water. Water has got high boiling point when compared to azeotropic mixture. Therefore, azeotropic mixture will come out. This 52.25% of azeotropic mixture will distill first. Then this component will come later. 47.75% of water will come later. Suppose if you take 98% alcohol and 2% water, what happens here? This 98% alcohol, 2% water, this requires only 4.5% water and 95 point. So some water, some the whole water will be absorbed by alcohol to form azeotropic mixture, and it leaves some amount of ethyl alcohol. Therefore, on distillation you can separate this into azeotropic mixture and alcohol in this case. In this case, azeotropic mixture and water. So therefore, when you distill type 2 liquid mixture, it is only possible to separate into azeotropic mixture and one of the components. This is a TX curve of type 2 liquid mixture. Now come to type 3 liquid mixture. So here in case of type 2 mixture, on fractional distillation what happens? First azeotropic mixture will come out and then one of the components will come out. That is the technique. Now come to type 3. Type 3 liquid mixture having negative deviation from Raoult's law. Negative deviation from Raoult's law. Example, hydrochloric acid and water. Here approximately 20% hydrochloric acid and 80% water forms azeotropic mixture. If you draw the boiling point and composition curve of this mixture, you will get reverse, opposite to that first type. What happens? First 20% like this, now 20%, 80% like this. This is again azeotropic mixture of this component, this TX curve. This is composition of hydrochloric acid and water. Composition, hydrochloric acid less volatile and more volatile. Less volatile is hydrochloric acid and more volatile is, comparatively more volatile is water. Now 20% hydrochloric acid and 80% alcohol, it forms a azeotropic mixture. So this is the temperature of azeotropic mixture. Azeotropic mixture. Therefore, and this is the vapor phase, this is the liquid phase. Similarly, this is the liquid phase and this is the vapor phase. Now, you take the mixture of hydrochloric acid and water, and if you distill, what happens? If you distill, you see the boiling point of both the components is less. Boiling point of both the components when compared to the azeotropic mixture. Azeotropic mixture has got high boiling temperature, boiling point, reverse to that of type 2. Therefore, when you distill this, first one of the components will come out. One of the components, either hydrochloric acid or water, will come out, leaving behind the azeotropic mixture. So you can separate that into azeotropic mixture and one of the components in excess. This is the TX curve of type 3 liquid mixture. So when you distill hydrochloric acid and water, it is not possible to separate hydrochloric acid and water completely, as in case of type 1. Only it can be separated into one of the components which is in excess and one of the azeotropic mixture. For example, if you take 50% HCl and 50% water, what happens here? Now, the composition of these two is 20%. 20% HCl and 80% water. But we have only 50% water. How much HCl is required there? About 10 to 12 ml of HCl is required for the formation of azeotropic mixture. This water combines with 10 to 12 cc of hydrochloric acid and leaving behind 36 to 38 cc of hydrochloric acid. Therefore, when you distill this mixture, first fraction will be hydrochloric acid. Because it is in excess, first hydrochloric acid will be distilled. Hydrochloric acid will be distilled, then azeotropic mixture. Second fraction is azeotropic mixture of hydrochloric acid and water. Therefore, in the separation of these two, only it is possible to separate into one of the components which is in excess and its azeotropic mixture. Now, if you take hydrochloric acid and HCl here, when you heat it, what happens? First one of the components, HCl, will come out first, leaving behind azeotropic mixture here. Therefore, only two types of distillate you will get. Suppose if say only 10% HCl is there and 90% water is there, what happens? How much HCl is required? 20% HCl means only about 40 ml of water combines with the 10% HCl, and excess water will be there. Therefore, when you distill such a mixture, excess water first water will come out. Pure water will be distilled first, leaving behind azeotropic mixture. So, azeotropic mixture will come out next. Therefore, it is possible, if this is the composition, it is possible to get two components, two distillate fractions. First one is water, because water is in excess, first water will come out. Now, you take the azeotropic mixture and heat it, first water will come out, leaving behind azeotropic mixture. Therefore, in this case, in type 3 liquid mixture, it is possible to separate into only two components. One of the pure components which is in excess, and another one is azeotropic mixture, and this is the technique used in the separation. Therefore, azeotropic mixtures cannot be separated by distillation methods. Azeotropic mixture cannot be separated by. So, azeotropic mixture means constant boiling mixture. A particular composition, it has a constant boiling. Anytime you distill it, each time you will get the mixture, that's why it is called constant boiling mixture. Azeotropic mixture or constant boiling mixture. In case of alcohol, 95.5% ethyl alcohol, 4.5 is the azeotropic mixture. In case of HCl and water, 20% HCl, 80% water is the azeotropic mixture. Azeotropic mixture is the constant boiling mixture which deviate from Raoult's, which will not obey Raoult's law completely. Therefore, by distillation method, azeotropic mixture cannot be separated. Other techniques are used to separate azeotropic mixture. That will come in the next topic. So, how to separate this azeotropic mixture? It is possible by other methods, not by distillation methods. So, this is about second type of binary mixtures, completely soluble mixtures. Now, let us pass on to the next type of liquid mixture, completely immiscible. Now, come to the third type, that is completely immiscible liquids. In case of the completely immiscible liquids, two components are entirely different. They are not miscible with each other. Pentane and acetic acid, two layers are formed. Not even they are completely different. Not even 1% is soluble in one another. They are entirely different. Bromobenzene and water. For example, vapor pressure of bromobenzene 125 millimeters. Vapor pressure of water 635 millimeters at standard temperature. So, total it is, if you see the vapor pressure, it is 760 millimeters, like that. So, therefore, they are completely independent. These type of liquid mixtures are completely immiscible liquid mixture. They are not at all miscible. So, these types of liquid mixtures, they have separate vapor pressure, but the total vapor pressure is the atmospheric vapor pressure and distillation. Therefore, they can be separated by steam distillation. And the pressure, partial pressure, vapor pressure of the component in the mixture, Pa is equal to XA, mole fraction, into P, total pressure of the mixture. Pb is nothing but mole fraction of B into P. Mole fraction of XA is nothing but Na by Na plus Nb. Mole fraction of Xb means number of moles of B divided by number of moles of B plus number of moles of A. Total number Na plus Nb, Na plus Nb. Now, if you divide these two by one another, Pp cancels, and Na, Nb cancels. Therefore, Pa by Pb is equal to Na by Nb. Na by Nb. Na is nothing but number of moles, weight of A by molecular weight by Ma divided by weight of B by molecular weight of B. Isn't it so? Therefore, Pa by Pb, Pa by Pb is equal to Wa by Ma into Mb by Wa. Wa into Mb divided by W by Ma by Wa by Ma into Wb by Wa by Ma, Mb by Wb. Isn't it so? Like that, what happens? Pa is equal to, by knowing the molecular weights and by knowing the partial pressure, we can find out the weight fraction. Weight fraction, Wa by Wb, weight fraction Wa by Wb is equal to Pa by Pb into Ma by Mb. So, this weight fraction can be determined by substituting these values. Weight fraction of the mixture of immiscible liquid per Wa by Ma is equal to the Pa into Ma divided by Pb into Mb. So, weight fraction can be determined by this calculation in case of completely immiscible liquids. So, these completely immiscible liquids cannot be directly separated. They have got less vapor pressure when compared to pure water. Pure water when compared to pure water vapor pressure, the vapor pressure of the mixture is less. That is why vapor steam is passed through this immiscible liquids. Through these immiscible liquids, when steam is passed through this, now one of the component which has this fraction will come out first, and then it can be separated by passing steam distillation because their vapor pressure will be reduced. So, this is the steam distillation method which can be separated very easily. So, that is about completely immiscible liquid phase. Two separate layers will be formed and that is separated by steam distillation. So, that completes binary liquid mixtures. Thank you very much.